Okay, so let's say we have two particles, particle A and particle B, and each one can either be spin up or spin down, as shown by these basis vectors. So 1, 0 means 1 in the basis vector showing spin up, and 0 in the basis vector showing spin down. Likewise with spin down, 0 in the basis vector showing spin up, and 1 in the basis vector showing spin down, and the same for particle B. We just write the subscripts A and B just to show which particle that state is for. Now, when we look at quantum entanglement, there are two types. There's symmetric, which means when we measure the state of one particle, so in this instance, we measure the spin of one particle, that would mean the other particle it's entangled with has the same spin. So for example, if we measured spin up on particle A, that means on particle B, we would also get spin up. On the other hand, antisymmetric entanglement means whichever we measure on one particle will cause us to get a guaranteed measurement of a different state on the other. So in this instance, if we measure spin up on particle A, that will cause us to get spin down on particle B, and vice versa. So what we want to do is we want to create 4 new basis vectors, one for each combination of both particles' spin states. So let's say for the combination where both spin states are up, we call that basis vector number 1. Then when the first particle has spin up and the second has spin down, we call that combination basis vector 2. Then when the first is spin down and the second is spin up, we call that basis vector number 3. And when both are spin down, we call that basis vector number 4. Now, what do these basis vectors actually mean? Well, let's say we had a quantum state, which would just be a line in this vector space. That quantum state, well, we don't know much about it. We don't have any measurements associated with it. Now, these basis vectors show the possible measurements our quantum state can have. Now, when we measure our quantum state, that means it will end up snapping to one of these basis vectors. And then whichever basis vector it snaps to, it will gain the result of that basis vector. So for example, let's say it snaps to basis vector number 2. That means when we measured our quantum state, the first particle had spin up and the second particle had spin down. So now let's look at the tensor product. So the tensor product takes in each particle's spin states and compares them to see which combination we have. And it does that by spitting out which basis vector from before we have. So let's do an example where the first particle, particle A, is spin up, and the second particle, particle B, is spin down, as shown by these two basis vectors. The way we apply the tensor product is we first of all take the first component of the first vector and we multiply it by the first component of the second basis vector, so 1 times 0, and that will give us 0. Now this means we have 0 amounts of the first basis vector out of our new 4 we have created, which means we have 0 amounts of the basis vector of both spin up, which means they are not both spin up, which is the case. We know, obviously, one is spin up, the other spin down. So then we take this first component and we multiply it by the second component of the second basis vector. And we write that result below. And obviously, in this case, 1 times 1 is 1. Oh, great. That means we have 1 lot of this second basis vector. And what does the second basis vector mean? It means the first is spin up, the second is spin down. And lo and behold, that is the exact case here. And obviously, if we do get the second component of the first basis vector, we times that by the first of the second, we get 0, 0 times 0, and then we do the bottom two, 0 times 1 is 0. So you take each component of the first basis vector and you multiply it by each component of the second, and then you do the same with the second component of the first basis vector, and you write them all in a column like this. Now, quite obviously, you can only have one of these states being measured at once. For instance, they both can't be spin up and spin down at the same time, which means in this example, as soon as we know which outcome we have, we can just set the others to 0. You don't even have to calculate it, because when we have one of the second basis vector, that means we know that it's one spin up, the other spin down. We can just immediately say the rest is 0. So, what are the Bell states? Well, Bell states are quantum states which exist in this basis we've created, which each have two outcomes. So, the two outcomes have two kinds. They can either be both symmetric combinations, which are the first and fourth basis vector, where both spin states are the same, or they can be anti-symmetric, which means they have both anti-symmetric outcomes, which means it'll be basis vector 2 or basis vector 3. Now, in quantum physics, you can write a quantum state as the sum of their outcomes. And obviously, in this case, each outcome is represented by a basis vector. So in our vector space, we can write our quantum state as a sum of these basis vectors corresponding to each outcome. Now, as we've said, the first Bell state has either symmetric outcome or either symmetric basis vector. So it will be a constant times the first basis vector plus a constant times the fourth basis vector. And similarly, with the anti-symmetric, a constant times the second basis vector plus a constant times the third basis vector. Now, the amount of each outcome or basis vector given by A or B squared gives us the chance or probability of when we measure our quantum state, that basis vector being the outcome. So, for example, A squared gives us the chance of when we measure our Bell state, which can either be the second basis vector or the third basis vector, it'll give us the chance of us measuring basis vector number 2. So, in this example, there are equal chances to all the outcomes. You know, for each Bell state with two outcomes, each outcome is equal, which means they're 50% each, which means when we said the coefficient or amount of each basis vector squared gives us the probability, that means the component of each basis vector squared, A and B squared, are both the same, are both 0.5, which means if you square root both of them, you can just take the positive and you have the square root of 1 over 2 as both of the coefficients. So that leaves us with our two Bell states, 1 over root 2, first basis vector plus the fourth basis vector, 1 over root 2 times the second basis vector plus the third. This being the symmetric one, showing both symmetric outcomes, and this one showing both anti-symmetric outcomes. But also, we have to include two more possible states where we add a minus in front of just one of these basis vectors. Now you may be wondering, well, why have we done that? Well, even though when we're talking about spin, as we are now, these both look the same, you know, if you square minus 1 over root 2 and plus 1 over root 2, you get the same probability for the fourth basis vector. In other bases, for example, position, momentum, energy, each of these two quantum states, or Bell states should I say, will give you completely different results. So we treat them separately as separate states here too. So that leaves us in total with 4 Bell states. Now you may be wondering, well, what happens if you add a minus to both components? Why is it just one? Well, if you add a minus to both components, you can factor out the entire minus, which means you'll get one of these two states with a minus in front. Now, what matters is not so much if the whole state is multiplied by a minus, it's when one of the components, one of the basis vectors, is positive and the other is negative. If they're both negative, it doesn't really make any difference. So it's only when one of these components is negative and not when both of them are. I hope that helps, and thank you for watching.